All right. I am going to jump right into some of the material from chapter 2. There are some very fundamental ideas discussed in chapter 1, as well as the system of SI units, dimensionality. You should definitely be reading everything in that chapter, but in the interest of time, I'll push ahead. So let's start out by taking a look at some familiar speeds and some not so familiar speeds, and deciding what each of these quantities has in common. So somebody who can run fast can easily run at a speed of about 10 meters per second. Just keep in mind, some people run the 100-meter dash in 10 seconds. 100 over 10 is the same as 10 over 1. And these are SI units. The meter is the physics standard definition of, or standard unit of length, and the second is for time. If you want to talk about how quickly sound moves in air, you could express that in meters per second, but it's a little nicer to say 1 mile every 5 seconds. And we can see something interesting in this number. You can read that as I just did. Sound travels about 1 mile every 5 seconds. Or look at the digits here. Doesn't that say 1/5? You could also say that sound travels 1/5 of a mile every 1 second. So 1 mile every 5 seconds is the same as 1/5 of a mile every 1 second. That's where that rule comes from. When you see lightning, count the number of seconds before you hear the thunder and then divide by 5. So if it takes 10 seconds after the lightning before you hear the thunder, 10 divided by 5 would tell you that the lightning was about 2 miles away. I think it was just last year near Long Beach, I was standing outside my home. Why am I telling you this? I saw lightning and heard thunder in less than a second. So I went inside. Car on a highway, 70 miles per 1 hour. You could also say 140 miles per 2 hours, because that's the same number. Here's a number you probably aren't familiar with. One of the things we'll talk about in this class is relative motion and whether or not there's such a thing as an absolute rest frame. Like, we like to think of ourselves as being at rest when we're sitting in a chair, and when we get on a train, well, now we're moving, we're an airplane. But you have to keep in mind that you're always moving with respect to the sun. You're on a big rock called planet Earth that's flying around the sun once a year, and that means you're moving really fast through space, 30 kilometers every second. That's something like 20 miles per second. So if you ever wonder, if you're in an airplane flying at 500 miles per hour, does that feel faster than 300 miles per hour? Your body really can't tell the difference, because your entire life, you've been unaware. Your body has not been notifying you of the fact that you're actually flying through space at 20 miles per second. A brisk walking speed, 3 miles for every 1 hour. And here's maybe the most remarkable speed of all. It's the very special one, which is why I put it in red. The speed of radio waves. Have you ever even heard of that speed, the speed of radio waves? I'm sure you've heard of the speed of light, and I chose to write it this way. Excuse me. I chose to write it this way because you may not have been aware that radio waves move at the same speed as the light which is visible to your eyeball. And that's not the only kind of electromagnetic wave that also moves at that speed. Ultraviolet light, infrared, well, that's a topic for another class. Lastly, the International Space Station. Every second, that thing moves something like 5 miles around planet Earth. So there's a range of speeds that are somewhat familiar to us, but this one is much greater than all of them. And one of the reasons the speed is so significant is, as far as we know, nothing can travel faster than that. And I shouldn't say nothing, because it's easy to show that the edge of a shadow, for instance, could travel faster than light, but you cannot transmit information with the edge of a shadow. So as far as we know, there's no way to pass information from one location to another any faster than light could do it. So if we look back at that list, every single one of these quantities has a quantity or another quantity in the numerator that's a distance, and a quantity in the denominator that is a time. Distance over time. Those are the units of, or that's the dimensionality of what we're calling speed. And in high school algebra, you may have used the letter D for distance. We are going to refine this a little bit and introduce a more precise quantity than just distance. So consider the real line. How about we call this the x-axis. We've got the positive direction and the negative direction. And here's Mr. Stickman standing at -2 on the x-axis, and he is displaced. He suffers a displacement over to x equals 5. So we'll call the initial position x sub I, and x sub f is the final position. Here's the definition of displacement. You've probably seen this before. Delta x, simple delta is used all over the place in math and physics. That just means change. So it's final minus initial. That's displacement in one dimension. Later, we're going to define displacement in 2 dimensions or even 3. And I'm showing you here that you don't need to be too attached to any particular notation. Sometimes we just have 2 important times in the problem that we're solving. We can call those times the initial time and the final time. But you may have 5 or 6 relevant times. If it's a problem about a rocket separating into different stages, maybe you have several important times in the problem, and you might need to use numbers. So this could be the position at time 2 minus the position at time 1, or it could be times 2 and times 7. Just get used to being flexible with notation. Okay, so from here on out, we will almost never use d over t. We'll talk instead about delta x over delta t displacement. And we won't dwell on this very much, but this is technically a final time minus an initial time. But I can't think of a single instance in the last several years of doing this class where we dealt with a negative time interval. We're always imagining that the arrow of time is into the future. So this is always just the time interval, and it's a positive number. So as an example, and this is not a notation that I will use frequently, but what I mean by this is the velocity between times 3 and 4. You would just take the position at time 4 minus the position at time 3, and then divide by the duration of that interval. So it's understood that this x coordinate happens at that time. x4 is where your particle or your person or your car or whatever, it's where it's located at time 4. Now, displacement does not always have to be a positive quantity. What if Mr. Stickman starts out at x equals 5 and ends up at -2? So he actually moved to the left. Let's look at that quantity now, x final minus x initial. Well, final would be -2, and then we subtract a positive 5. So we see that the displacement is the number -7. So it is possible for a displacement to be negative. Now, that does not mean that you have to end up on the negative side of the axis. It merely means that you moved to the left, or you moved in the negative direction. For instance, what if you started at 9 and ended at 7? 7 minus 9 is still -2. That's a negative number. It's possible to begin and end on the positive axis, but still have a negative displacement. And you can see that by the definition. Delta t, like I just said, is always positive, basically. And that means that the sign, SIGN, of the velocity is determined by the sign of the numerator. If your displacement is negative, that means that your velocity is also negative, your velocity during that time. Now, if you got pulled over for speeding and the officer said, ma'am, do you have any idea how fast you were going? If you had taken this class, you probably wouldn't want to say something like, I think my velocity was definitely -65 miles per hour. Because the cop's going to think that you're being a smart ass. Can I say that? Excuse me. A smart aleck. Speed refers to just the absolute value of the velocity. It's how fast you were moving. So that's the relationship between those two quantities, at least in one dimension. If you know the velocity, just take the absolute value. That's speed. Okay. This is the first time, unless you've read the chapter already, this is the first time you're seeing a very important tool throughout the semester, especially in these first several chapters. This is a position versus time graph. If you've never taken a physics class before, you're accustomed to thinking of this as the y-axis and this as the x-axis. Well, usually we're doing something different in this class. We do look at y versus x graphs, but often we're talking about position versus time. So let me just pick a particular point on the graph. I'll put the laser pointer right here. Right here, okay. If I drop straight down to the t-axis, that tells me that this event happens at t equals 5 seconds. If I move over perpendicularly to the x-axis, I see that the person is at the 60-meter mark. I'm just using the grid lines there. So this person was at 60 meters from the origin at a time of 5 seconds. That's the meaning of this graph. if somebody is moving, if it's a person we're talking about, walking away from the origin, so if they're moving in the positive direction, then their motion on the x versus t graph would look something like this line. So what is the significance of this line? Well, that tells you, I should say the length of this line segment tells you how far the person is from the origin when they're right here. The length of this segment is their distance from the origin. And you can see that as we move this way, as time increases, we're moving along this, this line here. The length of this line segment is increasing. That just means they're getting farther and farther from the origin. So I'm being very deliberate right now. Hopefully this is a little too slow for you. That would be good. And you could just put me on 1 1/4 speed or double speed on YouTube. If this person is moving in the negative direction, that's not necessarily away from the origin. What if they started out over here and moved in the negative direction? They would actually be moving towards the origin. So it's not that they're moving away from the origin per se, it's that they're moving in the negative direction. And that means that their x-coordinate is decreasing. So let me just show you what I mean by that. With, decreasing, if you've got a number that's already negative, like down here, if you're at -50 for your x-coordinate, and you move down to -100, in the math sense of the word, your x-coordinate is decreasing. It's decreasing from -50 to -100. It's becoming more negative. Now, the absolute value of the x-coordinate is actually increasing, is it not? If you continue along this trajectory, this line segment is increasing in length. So their distance, we say that their distance from the origin is increasing, but the x-coordinate is decreasing. So anytime your x-coordinate is decreasing, you have a negative velocity because it means you're moving to the left. That's if you're going to the right positive. So on this real number line, motion to the left is negative velocity or corresponds to negative velocity. And your distance from the origin may be increasing or decreasing. When you're over here moving in a negative direction, your distance is actually decreasing, your distance from the origin. When you get to the other side, your distance from the origin is now increasing, but you still have a negative velocity because your x-coordinate is still decreasing. Let's take a look at a simulation now. This is one of the PhET simulations, Physics Education Technology, although I got this from a different website. Check it out. We've got this little guy that we can control. We can make him do whatever we want. Well, not whatever we want, but we can make him move around as we wish. So I'm going to hit record, and then I'll just grab him with the mouse and move him around. And as I do that, for starters, pay attention to the plot of his position versus time. And I'm trying to use fluid motions. Stop, move back, stop at the origin, move to the left, move to the right. Go a little slower now, and then fast. Oops, I hit a wall. So let's take a look at the position versus time graph. Now, for these first few seconds, we see, in fact, all the way up to about 2 seconds, his x-coordinate is 0. It's not changing. That means he's at the origin and he's not moving. As soon as he passes around the 2-second mark, his x-coordinate begins to increase. See, it's moving towards larger and larger positive values. That means he's moving to the right. And if he's moving to the right, what is the sign, SIGN, of his velocity? Well, we just established that motion to the right along the x-axis corresponds to positive velocity. And that's why when we go down to a graph of velocity versus time, it may be jagged, but overall you see that the average value of the velocity in here, oops, I need my laser pointer. I always forget that. Nope, this is not PowerPoint, never mind. Despite how jagged it is, you can see that the average value is some positive number. Now, once he gets here, he appears to be moving back in the other direction. See, his x-coordinate is now decreasing. It reaches 0 again, and then it goes into the negative direction. So he's moving to the left. And that is why when we go down to the velocity versus time graph, we see overall negative numbers for velocity, despite how jagged they are. Now, the jaggedness here is an artifact of the way I'm producing the motion. I'm just dragging my finger across the mouse pad, and that's not a very smooth motion. The sensor must be picking up tiny fluctuations to the left and the right. So it's not a clean signal, so to speak. What's going on right here? You might recall at some point I accidentally dragged this guy into the wall, smashed him into the wall, so we couldn't move for a while. And that's why his x-coordinate is not changing. And if your position is not changing, isn't your velocity zero? You're neither moving left nor right. And that's why when we look down here, we see that, yes, indeed, the velocity is zero. So you can actually infer the height of this curve, the velocity curve, at any point in the motion by looking at the position versus time graph. All the information contained in this graph, believe it or not, is already contained in this graph. It's kind of interesting. And the converse is not true. You cannot extract all the information in the blue graph by looking at the red graph. And this is really a calculus idea. When you integrate velocity, there's a constant of integration, and that, we'll see, that corresponds to your starting point. So this graph can give you a lot of the information about the blue curve, but not everything. The red graph will not tell you what your starting point was. Our starting point was actually the origin. But the blue graph will give you everything you need to know about the red graph. And later, very shortly, we're going to see that what I'm talking about is the relationship between the derivative and the integral. Okay, now, can we contrast the motion right here? And I really hope you can see my mouse right now, or the pointer arrow. Can we contrast this motion with, for instance, this motion? In both cases, the x-coordinate is decreasing, right? It's positive, moving towards zero, then it's becoming more negative. Same thing over here, the x-coordinate is positive, moving towards zero, and then it goes negative. But this is steeper, is it not? So in a moment, I'll show more precisely that the steepness tells us something about the speed. And sure enough, when we go down to the velocity curve, the velocity or the speed is low enough, or it's far enough on the negative side that it actually disappears off the graph. And that's not true over here. Here, the velocity is something like, looks like -10 maybe. Okay, so you should, maybe you should pull this up and mess around with it. Make sure you can understand the relationship between the x versus t graph and the v versus t graph. I'm still going to talk more about that. What else can we do with this guy? There's an option for functions. Let me reset. So their default function here is a sinusoidal function. Let's see what that looks like. He's just oscillating back and forth, passing through the origin and then coming back. Now, I don't know what's up with this little blip here in the acceleration curve. We still have to get to that. But once again, let's just observe right here. You see how for a brief moment of time, his x-coordinate is not really changing. If I go from here to here, the x-coordinate is practically the same. If your position's not changing, you're not moving, your velocity should be zero. And sure enough, when we drop down to the v versus t graph, we see that the velocity is zero right here. It's crossing the t-axis. Right here, the x-coordinate is negative, but it's rapidly increasing. It passes through zero, it's still increasing. So that means that the man is moving to the right. That would correspond to a positive velocity. And yes, the velocity here is positive. It's on the high side of zero. So any position versus time graph that you can think of would allow you to infer the velocity versus time graph. That's the relation between the two. And now I want to mess around with entering a couple of functions here just for fun. And to be instructional, let's start with quadratic motion. So I'm going to tell this guy to move as follows. I'm going to move with the square of the time. So t squared, that's easy, right? After 5 seconds, 5 squared would put you 25 meters from the origin. But it turns out this is going to get him moving pretty fast. So I'll put a coefficient out front, slow him down, 0.2 times t squared. Let's try that. He's starting out slow, and then he's picking up the pace until, uh-oh, I forgot about the wall. Oops, sorry, bro. Can I zoom in? Yeah. What do you notice about the position versus time graph? See how it's scooping upwards? So in a moment, we're going to look more precisely at slope, but you can see how the slope of this graph is getting steeper, and then it stops increasing, x versus t, or the position stops increasing. That's when he hits the wall. And if the slope is increasing, perhaps the velocity is increasing. You saw that just now, right? Wasn't he getting faster and faster? You can see that right here. The absolute value of the velocity is increasing. Just look at the distance from the velocity graph to the t-axis. Look at how that is getting larger until here when he hits the wall. All right. Now, okay, this is honestly, this is not instructional at all. I just want to do something fun. What if we launch this guy exponentially into that wall? Let's see what that looks like. Since we can make him do whatever. I'll hit use function and let's go with exp. That means e to the base of the natural logarithm raised to the t power. And I don't want him to get going too fast, so I'll put a little number up front. How about 0.2 again? Otherwise, he'll pick up speed too quickly. Let's see what happens. Yeah. Okay, he's gaining speed a little more slowly than I expected. Let's do something just a little more dramatic. Oh, yeah, if you're going to use this, I recommend hitting pause first, then reset, right? Then hit the use function button if you're going to enter something like that. E to the, I'll just go with E to the T. Okay, that's kind of amusing. Now check this out. Is there a way to make this guy move to the right? And then turn, you know what, there was something else I want to say about that. This is something you learned in calculus. E to the, how about I, yeah, just leave it E to the T. Take a look at how the position versus time graph compares to the velocity versus time graph, and how that compares to the acceleration versus time graph. I know we haven't talked about acceleration yet, but we will. And unfortunately, the vertical scales are different. See, they went from -10 to 10 here, but they went from -12 to 12 for the velocity. If the ranges were the same for all three, you would see that the graphs are identical. Because maybe you remember, what can you do to the exponential function to get a different, well, to get the same function right back? Hopefully you remember that it's the only function which is its own derivative. So really what we're talking about is differentiating with respect to time. All right, watch this. I'm going to see if I can make this guy turn around. So I'll start out with a quadratic function. This is going to dominate it first, but then I'll put negative 0.02 times e to the t, because what's going to happen is for small values of t close to 0, what's e to the 0? Isn't that 1? And 1 times 0.2 is a small number. 0.02, I should say, is a small number. So at first, the t squared term is going to dominate, but by the time you get to later times, it sounds redundant, the exponential term will be much larger. And since I've got this negative out front, that ought to make him go towards increasingly negative values. In other words, turn around and go left. Let's see if that actually works. Oh, I don't know what I did wrong there. Let me try this again. Reset. Use function. What did I say? 2 times t squared minus e to the 0.2 times t. Okay, I think what you have to do is tap out of the box in order to actually input the function. That's kind of annoying. And we'll try again. You know what I did wrong? I was supposed to get rid of the wall. I'll get it right this time. All right, I'm going to copy that. Don't forget to pause, reset. If this is boring you, please just move on. Fast forward. Get rid of the walls, use function, input my function, tap out of the box, and now let's see. All right, so he's quadratically moving to the right, and then, where'd he go? I really expected him to come back. Let me figure this out. Okay, here's one that works. Just go with t squared, and instead of having that 0.2 in the argument of the exponential function, just put it out front. So he starts out moving to the right because of that quadratic function, but then the exponential term becomes, whoa, there he goes. And I've got one more that's kind of fun. Here, I gave him the quadratic t squared that I'll move him to the right at first, but then this exponential with the minus sign out front becomes dominant, and that'll launch him back toward the left. But then I've got another exponential function with a very small coefficient out front, but e to the 2 times t. So at large times, e to the 2t becomes really large, a huge number, and so it overcomes this coefficient out front, and that should launch him back to the right. Let's see if this works. Whoa! Wait for it. Whee! Back to business. Let's use a spreadsheet to examine this motion in detail. We can easily calculate average velocities over successively smaller time intervals with the spreadsheet. So I'm going to take a look at this function, x coordinate equals time squared. So what I've done here is first create a list of times. And this looks a little confusing at first. I've got a column of integers here. Basically, my times are 3 plus 1 second, which is 4, 3 plus a half of a second, which is 3.5, 3 plus a quarter of a second, which is 3 1/4, 3 plus an eighth of a second. You get the idea. So I'm adding successively smaller time intervals using powers of 1/2 to the number 3. And then let me bring back the formula bar here. You can look at the formula that I entered here. In this cell, I'm telling Excel to say, hey, or I'm telling it to take the time. See how it says B2? B2 would be this cell right here. Take that time and raise it to the second power. In other words, square it. And if I go down, I see that I'm now taking this time, 3.5 seconds, and squaring it to get that x coordinate. So all I'm doing is just computing the position coordinates at all these times according to this rule over here, x equals t squared. But the interesting part is this column, because just now I defined velocity as displacement over time, how far you move, roughly speaking, divided by how long it takes you to do that. So what I'm doing is, let's look at the formula here. C2, that would be this x coordinate minus 9. Well, 9 is the x coordinate at what time? What number squared is 9? That would be time t equals 3 seconds. So 9 is where this particle is at the 3-second mark. And then I'm dividing by B2, which is 4 seconds, minus 3 seconds. So all I'm really doing here is implementing delta x over delta t, but my initial position and my initial time are 9 meters and 3 seconds, respectively. I hope I'm not confusing you there. And so I'm always using as my starting time 3 seconds, and my starting position would then be 3 squared or 9 meters. So this first quantity here, which comes out to 7, that is the velocity over the time interval between 3 seconds and 4 seconds. Maybe I should put t underscore f for final. Whoops, go with the lowercase f. All right, so these are all my final times. So delta x over delta t, this is the velocity from t equals 3 seconds to t equals 4 seconds. This is the velocity from t equals 3 seconds to t equals 3.5. This next number is the velocity over the interval from 3 seconds to 3 1/4 seconds. So I'm computing delta x over delta t for smaller and smaller time intervals. And you see that all these numbers are similar. They're also decreasing, and they're decreasing monotonically. You see how every number is smaller than the last? It never goes back the other way. And it appears to be approaching a limit. So this is a simple exercise, but if you've never done this, it really helps you understand what the derivative is. You remember the difference quotient from calculus? The change in one variable compared to the change in a variable that it depends on. And you look at the ratio of those two changes. So as I go to smaller and smaller time intervals, I mean, look what's happening to the time. You know what I should do here is insert another column, and I'll call this column delta t. Symbol. I'll call this column delta t, and that would just be the final time minus the initial time, which is always 3 seconds. And I'll ask Excel to compute that for all these final times. And I could do the same with delta x. Let me just copy paste here. Call this column delta x, and that would be the final x coordinate minus 9, because I'm always using an initial time of 3, which is an x coordinate of 9. Okay, so I'm looking at the velocity over smaller and smaller time intervals. Do you see how the time interval is headed towards 0? By the time we get here, it is 0 out to 7 digits. If I were to show more digits, let me do that real quick, then we would see it's not actually 0. Where's that button? Right here. And you'll be using some of this later in lab. Okay, I have to stretch this out so we can see all the digits. I don't know how many digits Excel can show, but the numbers are not actually 0, but they're getting closer to 0. So the time interval is going to 0. What is happening to the displacement? I mean, how far can you move in a fraction of a second? Not very far. So as you look at smaller time intervals, of course, the displacement also gets smaller and smaller. So despite the fact that delta t is going to 0 and delta x is going to 0, their ratio does not. I'm hoping that this is boring you because you already know this, but this is really the crux of what a derivative is. You let both quantities go to 0, and you're really asking, well, what's the meaning of 0 over 0? Because that's kind of undefined, right? But the limit is not undefined. The limit of the quotient really is approaching a particular number. I hope that's sinking in. All these delta x's are going to 0, and all these delta t's are going to 0, but the ratio of the two is approaching a limit. And I think it's fairly obvious that the limit is 6. And you guys already know how to take derivatives. I'm going to show in a moment that, that the velocity really should be the derivative. So d dx, the derivative of, d dt, the time derivative of t squared, we all know that is 2t, right? You bring down the power. So if velocity actually is the derivative of position, since the position is given by t squared, the velocity at any time should be given by 2 times t. And if you evaluate that at t equals 3 seconds, you get 2 times 3, or 6 seconds. Pretty cool. So this is sort of philosophical, but suppose we were trying to answer this question. How fast is this thing going? You know, if this describes a car, for instance, how fast is the car going at t equals 3 seconds? How fast is it going at that exact instant? Here's why that's a tricky question. Let me go back to, I'll go back to that simulation. I put t squared back into the function bar. Let him go, let him smash into the wall there. And I'll zoom in. Maybe you were able to tell the answer to this question by just watching what happened or from looking at the graph. Would you agree, let's play back here. Would you agree that this guy is getting faster all the time? Maybe it's not real clear because it's not the most fluid simulation here, but how do I go back? It appears to me that he's always getting faster and faster. The motion looks a little jerky, that's just the computer. So if he's always getting faster, if at any point in time he's already going faster than he was a moment ago, and how long is a moment? Well, as small as you like, then how long does he spend at any given speed? Like, let's say his speed at 3 seconds really is 6 meters per second. How long does he spend at that speed? Does he spend a full second at that speed? Clearly not. Does he even spend a half second going 6 meters per second? What is that amount of time that he spends going 6 meters per second? Maybe you're realizing there's no amount of time. You can pick any tiny number you want, 1/10 of a second, 1/millionth of a second. If he's always getting faster, then there's no finite amount of time at which he's moving 6 meters per second. So what does it even mean to say that somebody's moving at 6 meters per second? Like, if you can actually tell the cop that you were driving at 65 miles per hour because while you were driving, you saw the needle on the speedometer hovering over the number 65 and it stayed there for several seconds, or maybe it was there for a whole minute. then you actually spent a finite amount of time at that speed. That's why you can say you were going that fast. If you don't spend any finite amount of time going 6 meters per second, how can you even say that you were going that fast? What does that even mean? Well, the answer is really in what we just did in the spreadsheet. So let me go back to that. What I did in this column is to compute, technically it's called the average velocity. In previous slides, I just said velocity. Well, technically, this is really the average velocity. If you take the total displacement between the t equals 3 second mark and the 4 second mark, if you take the total displacement and then divide by that time interval, that's actually the average velocity during that 1 second interval. And then here, I took the total displacement during a half second, from 3 seconds to 3.5 seconds, and then divided by that half second. And I got a different average velocity. So what I'm doing is computing the average velocity over smaller and smaller time intervals. And we see that the average velocity is approaching a limit. And that is what we call instantaneous velocity. So that's how we answer the question. It seems like a conundrum. How could you even say you're going any particular speed if you spend no time going that speed? Well, it's because you look at your average velocity over a finite time interval and you let that time interval get shorter and shorter, and it approaches a limit. So if you can't use the derivative, if you can't talk about instantaneous rates of change, then you can't really define instantaneous velocity. Let's look at a graphical interpretation of that same result. So I went to the Desmos site. They've got some awesome free graphing calculators. Made a parabola. Notice I've labeled the axes. The vertical axis is my x coordinate. Horizontal axis is my time in seconds. And I couldn't actually use the 1 second time interval and smaller that we looked at in the spreadsheet, because then it's all crowded together on the graph. So instead, let's look at this particle's displacement from the 3 second moment in time to the roughly 7 seconds. So it starts out, remember it's t squared, so 3 squared is 9. It starts out at 9 meters from the origin at t equals 3 seconds. And then by the time it gets to t equals 7 seconds, 7 squared is 49, it's almost 50 meters from the origin. And we were using the definition of average velocity to be delta x over delta t. Well, delta x, this horizontal line represents the x coordinate. Final x coordinate is 49. Initial x coordinate was 9. So the length of this line segment represents the absolute value of the displacement, delta x. This is what you might call the rise, and this is the run. So delta x over delta t is really rise over run. In algebra back in high school, you were accustomed to thinking about that as delta y over delta x, but we've changed the names of the axes. So delta x over delta t is rise over run. We all know that's the slope. Slope of what? Well, you see this line that I've passed between the final point on the graph and the initial point? That's called the secant line because it pierces the graph at 2 places. It's a secant line. So it's really the slope of the secant line. So to summarize, the average velocity between 2 times on a position versus time plot can be visualized as the slope of the secant line. Average velocity is the slope of the secant line. And now let's do the same thing I did in the spreadsheet. Let's examine this for shorter and shorter time intervals. Instead of this 4 second time interval from 3 to 7. So I should have put this slide up. Rise over run is average velocity. And I'm using this over bar to denote average. Your book doesn't always do that, but that's common. Over bar means average. And this subscript x emphasizes that we're talking about velocity along the x-axis, because later we're going to look at 2-dimensional problems where we've got an x velocity and a y velocity. Okay, see what I did? I just shortened the time interval to less than 3 seconds. And that, of course, means that the displacement is smaller as well. And oops, I didn't draw this very well, did I? The final point should really be here. So delta x should look like this. You'll have to forgive me. But you can see that the slope has changed. I've drawn a different secant line, the secant line right here. It has a different slope. Just like in the spreadsheet, as I go down the column, those average velocities are changing. Changing yet again. This secant line has an even lower slope but it's not changing drastically. They appear to be bunching up. These lines are going to start bunching up to a limiting line. And hopefully you know where this is going. What is that limiting line? Eventually we get to a point where our secant line really only touches the graph at one point. That's called a tangent line. So the limit of the secant line for a fixed left endpoint, the limit of the secant line is the tangent line. That's the graphical way of saying something that you already know from calculus. So I've got the 3 bars here. That's the definition symbol. It's stronger than just an equality. Notice the overbar is gone. Without the overbar, this is supposed to be read as just velocity, which is short for instantaneous velocity. So unless you specify the overbar or AVE for average, what you're talking about is instantaneous velocity, and that is dx over dt. In your calculus class, you might say the derivative of x with respect to time, or the instantaneous rate of change of position with respect to time. That's obviously a mouthful, which is why we say things like dx dt. But let this not be lost on you. Dx dt it's a fantastic notation that was bequeathed to us by Leibniz, I think. It means delta x over delta t for teensy weensy infinitesimal dt's and dx's. Right? Don't forget that the d means delta. This is really a time interval that's infinitesimally small. How small is infinitesimal? Well, it's smaller than a millionth. It's smaller than a billionth. Think of the smallest number you can. It's smaller than that. It has no, it's infinitesimal. That's what that word means. So dx dt means delta x over delta t in the limit as delta t goes to 0. Right? So another way to put this whole thing is instantaneous velocity is defined as the limit of average velocity as you compute the average velocity over smaller and smaller time intervals. So me moving from one secant line to the next until they all start to bunch up and reach that limiting tangent line, that is equivalent to going down that last column in the spreadsheet. And the numbers were getting closer and closer to 6. And what is the significance of 6, or where do we see the number 6 in this graph? That would be the slope of the tangent line. So there's another important statement. The derivative gives you the slope of the tangent line. Okay, hopefully that's clear. You may have known all of that already, but it's nice to see it all pulled together. Personally, I didn't really understand the derivative and the integral until I took physics, because velocity, acceleration, those are archetypal derivatives. In fact, the person who developed these ideas originally, I think, which was Newton, I'm sure he was thinking about these things when he did it. It's probably the most intuitive derivative, because we all know what it means to move. Okay, I did that already. What can we say about this picture? Now that we understand that the slope of the tangent line gives us instantaneous velocity, it's easy to connect these two graphs now. We can see that the slope is increasing as we go from one section to the next, and that means that the velocity should be increasing. So sure enough, when we drop down from here, we see that the velocity during this time interval is a greater number than it is during the initial time interval. Isn't this slope steeper than this slope? And hence the velocity is greater than it is here. They're both positive velocities because the slopes are both positive. Now why is this graph flat in here? Which means that the velocity is constant, right? It's not going up, it's not going down. There's a constant velocity during this time interval. Well, you can see that here because the slope is constant. It's got the same steepness throughout. That's equivalent to saying that a line is a special curve where the slope is constant. You can pick any 2 points on a line, compute the slope, and you'll get the same answer. Now what's going on here? You can see that it's gradually scooping upwards. So the slope is continuously increasing in this time interval. And that means that the velocity is increasing. If you could draw a tangent line to this curve, the slope of that tangent line is increasing on the way to this time right here. That is why the velocity is steadily increasing. So like I said earlier, all the information in this graph is contained in this graph. If you take the derivative with respect to time of the position versus time graph, you will get the velocity versus time graph. As for notation, here's something your book does early on. They go with this generic letter S. I usually just say X versus T when I'm introducing this stuff, but I guess your book doesn't want you to get too boxed into thinking that it's always motion along the x-axis. Everything we're saying would hold equally true for motion along a y-axis or any axis, really, as long as it's motion in a straight line. So they call it the S versus T graph. S is just some generic coordinate. Instead of calling it the x-axis, call it the s-axis. Okay. So velocity, and I'm contradicting what I said just a moment ago. This is really a finite displacement over a finite time interval. That's average velocity. I really should have the over bar here. I was being lazy. So I've written that the velocity here is positive because you can see that the slope is positive. Okay, what about negative velocity? Well, here's another position versus time graph, and I'm calling it the x-coordinate. Time moves, the future direction is this way. So we're moving along this graph, and we've got an x-coordinate of 5 at time -4 seconds. And then we go all the way back to an x-coordinate of 0. So if you're at 5 and you end at 0, weren't you going to the left, back towards the origin? So your displacement was negative. And then using the definition of velocity here, if you plug in a negative displacement, that would be a negative velocity. Can you tell from the graph immediately that the velocity is negative? Remember, this is a position versus time graph. What is the slope of x versus t? It gives you velocity. The slope of the tangent line to an x versus t graph is instantaneous velocity. And since the slopes here, all the tangent lines would have negative slopes, we know that the velocity is negative. Simple as that. Over here, the slope is positive. Displacement's positive. That's positive velocity. Okay, so everywhere in here, this particle is moving to the left. Everywhere in here, this particle is moving to the right. What is happening right here? What can you say about the slope of the tangent line? It is 0. So what does that tell us? Well, the slope of position is instantaneous velocity. Evidently, the velocity here is 0. We're neither moving to the right nor to the left. Just for a moment, we're stopped. Okay, perhaps that's enough about velocity. Let's move on to acceleration now. And I'm going to point out right now, acceleration in this class does not have quite the same meaning that it does in the vernacular, in the colloquial sense, which is to speed up. Usually when people use the word accelerate, they're talking about speeding up. And if they want to say slow down, they say deceleration. Well, in this class, acceleration is really going to be any change in your velocity, any change in velocity. Right now, we're just talking about one-dimensional motion. Here's a jet that's being accelerated by, I think there's one of those catapult tethers here. It's hard to see. So this one's speeding up. This bird's probably slowing down before it lands. What an awesome picture that is. Okay, so let's see if we can analyze this to death. We've already seen, and this is sloppy, they say distance here. This should really say position, unless they're talking about the absolute value here. No, this should really say position. We've already talked about how the slope of this graph gives you this graph. All the information in this graph is contained in this graph. Just take the slope, boom, now you've got this graph. Well, we're gonna see that you can do the same thing again and get the acceleration graph. Taking the time derivative of the velocity versus time graph will give you the acceleration versus time graph. So once again, let's see here. You see that the slope is gradually increasing and it's always positive. That's why here the velocity is always positive and it's increasing. What happens in here? See how the slope is roughly constant in here? That's why the velocity is constant. The velocity is still positive in here, but do you see how the slope is leveling off and it approaches 0? What is the slope of position versus time? That's velocity. So the velocity is going from positive values back down to 0. See how the slope is 0 here? Velocity is 0. Then the slope becomes negative. We're moving back towards the origin. We're moving in the negative direction, really. That's the important part. And that's why the velocity is negative. And this graph's a little misleading because they're saying that the velocity is decreasing until here. But it looks to me like the slope has already stopped changing here. But do you see how from here to here, the slope has become a little bit more negative? That's why they're showing the velocity getting more and more negative. Now, right here, are we stopped? See how the slope goes from negative to positive? Does that mean that we're stopped right here? No, because I'm looking at the V versus T graph. It's only when the position versus time graph has a slope that goes from positive to negative that you're stopped in the middle. So don't be misled. The statements that apply to the X versus T graph are not necessarily going to apply to a V versus T graph, for instance. This just means that my velocity is decreasing, and now it's increasing again, but it's still negative the whole time in here, is it not? All these velocities are negative because the slope up here is negative the whole time. Now finally, the slope goes back to 0. The position is not changing. That means you're not moving. That means your velocity is 0. And that's why we see this. Now the next slide, you can confirm all those statements. Like I said, this is not perfect. This should probably be, well, maybe it is. Maybe they've just scaled up the vertical axis. In any case, let's see now if we can connect these two. I haven't defined acceleration yet. We'll do that in a moment. But you have some intuition about what it means. So the velocity here is increasing. It's positive and it's increasing. As you can see right here, the slope is increasing. That means you're speeding up. And we at least know that acceleration, or that if you're speeding up, that's one example of acceleration. So you can see that the acceleration here is not 0. It's a positive number during those first few moments. And it's constant. See how the value of the acceleration is constant? It's no coincidence that the slope of the velocity graph is also constant. Constant slope, constant acceleration. Here, the slope is also constant, but it's a special constant. It's 0. There's no slope for velocity. That means no change in velocity. Well, if your velocity is not changing, that means you're not accelerating. That is why we see an acceleration of 0. Now, what's happening here? The velocity is decreasing. It's going from positive values to less positive values to 0. That means you're slowing down. So it's no surprise that you are accelerating. And in this case, the acceleration is negative. But I want to point out now, acceleration does not always mean, or excuse me, negative acceleration does not always mean that you're slowing down. In this instance, it does mean that you're slowing down. Really, a negative acceleration just means that your velocity is decreasing. That's all it means. I'll repeat that. Negative acceleration means that your velocity is decreasing. Because let's look at the other side of the 15-second mark here. The velocity is still decreasing, is it not? Right here, the velocity is a negative number. Now it's more negative. Now it's more negative. So it is decreasing. That's why the acceleration is still negative. But what's happening to your speed over here? If you're going, let's say, negative 10 meters per second, and then you're going negative 15 meters per second, your speed, which is the absolute value of velocity, is actually increasing. So it's possible to have a decreasing velocity, but an increasing speed, despite the fact that you have a negative acceleration. That's confusing for people at first. So in this instance, the acceleration right in here between this time and this time, the acceleration is negative, but you're actually speeding up. The significance of negative acceleration is that your velocity is decreasing, negative decreasing, positive increasing. So let's look right here. We're told that the acceleration is positive, and sure enough, the velocity is increasing. Even though the velocity is negative, it's increasing. Now, what about the speed here? Do you see how the absolute value of the velocity is decreasing? That's confusing, right? The velocity is increasing, it's becoming less negative, but the absolute value of the velocity is decreasing. So you do have a positive acceleration, hence increasing velocity, and yet you're slowing down. So, converse to the other statement, you can have a positive acceleration and actually be slowing down. So in this class, in the language of physics, positive and negative acceleration, that doesn't tell you that you're speeding up or slowing down necessarily. It tells you whether your velocity is increasing or decreasing. Simple as that. If if that's not sinking in, take some time to look at this graph and maybe think about some other examples. Okay, you've heard some commonly quoted accelerations. Let's talk about maybe one of the most obvious ones. I just pulled up some data on a Porsche, what have you, and they're using kilometers per hour. But you often hear something like this. Oh, I've got this sports car. Not me, of course. My Corolla won't do this. But this Porsche will go from 0 to 60 in 2.8 seconds flat. What do they mean by 0 to 60? Usually we're using, in the United States, at least, we're talking about miles per hour. So the velocity or the speed increased from 0 up to 60 miles per hour in this amount of time. So we'd like to look at the ratio of those two quantities, the change in the velocity compared to the change in the time. And right here, they're telling us 0 to 100 in 2.8. 100 kilometers per hour is about 60 miles per hour. That's where I got that number from. So acceleration, loosely speaking, is the rate of change of velocity with respect to time. You have to specify the other variable. If you just say rate of change, well, rate of change with respect to what? Very often we just kind of understand that it's the rate of change with respect to time. It's changing in time. But later we'll look at rates of change with respect to position. If this car is driving in a straight line, then as its position changes, so does its speed. You could also talk about how the speed depends on its position. It's a little easier to think about how the speed depends on time. So the definition is almost identical, or it is identical really, just different variables, to the definition of velocity. Velocity was delta x over delta t. Acceleration is now delta v over delta t. So this would technically be what, if you've been paying attention? I shouldn't just say acceleration, I should say average acceleration. If you compute the change in velocity over a finite, not an infinitesimal, but a finite time interval, then you're really talking about an average velocity. So again, delta means final minus initial. My final velocity is 60. My initial velocity is 0, presumably. If I enclose those in parentheses, then I can put the units outside miles per hour. This is better than writing mph because it emphasizes that it's a ratio, miles per hour. And if you've never noticed this before, there's a reason why ratio and rate look very similar. Those words have the same root. A ratio, or I should say a rate, is a ratio. This is the rate of change of velocity with respect to time, and you'll notice it's a ratio of the change in one variable compared to the change in the other. That's the study of calculus, right? How changes in one quantity relate to changes in another quantity. Now, technically, delta t is final time minus initial time. So if you started your stopwatch when the car began driving, like when the driver hit the gas pedal, then your initial time would be 0, and your final time would be 2.8. Normally, we don't have to think explicitly about delta t. It's just whatever the time interval was. Okay, well, this is just a number, right? We can reduce this 60 divided by 2.8. You can throw that into the calculator, and that comes out to be this number, 21.4 miles per hour per second. So you could say that a Porsche is capable of accelerating at about 20 miles per hour per second, which is very intuitive. What does that mean? It's on its face. It just tells you every second your car is speeding up by about 20 miles per hour. So when you first hit the gas, the car's not moving yet. 1 second later, it's going about how fast? 20 miles per hour. After it's been driving for 2 seconds, it's now going about 40 miles per hour. After it's been driving for 3 seconds, it's going about 60 miles per hour. So the longer way to say it that would be clearer to somebody who hadn't studied this before would just be to say that this car is capable of going 20 miles per hour faster every second. Right? As simple as that. Now, we treat units the way we treat variables in algebra or symbols. So it would be just as valid. You know how a divided by b divided by c is the same as a divided by b times c? I referenced that in the error propagation video, I think it was. A divided by b divided by c is the same as a divided by b times c. That's what I've done here. So you could also say it's 20 miles per hour second. 20 miles per hour second. That's the same as saying 20 miles per hour per second. Obviously, the original way of expressing it that I talked about makes more sense intuitively. Okay, now this is not an SI unit of acceleration. We've got mixed units here. First of all, miles, those are imperial units. We'd like to use the meter, and the hour is not the SI unit of time. That's the second. So this is our first example of conversion. Very simple. You've probably seen it in chemistry, but here is an important point. This is a valid statement. By definition, a mile is this many feet. If I were to divide both sides of this equation by 5280 feet, what's 5280 feet divided by 5280 feet? That's 1. And that would give me, I guess what I did here is actually divide by 1 mile on both sides. 1 mile divided by 1 mile is 1. So saying this is the same as saying this. If 5280 feet really is the same as 1 mile, then when you take their ratio, you just have the number 1 with no units. That may seem confusing to you because how can these units cancel if they're not the same? It's not how it works. We're forcing these to be the same by definition. And when you write it this way, it's useful as a conversion factor. You can multiply by this conversion factor. You'll see what I mean. Here are the other two that we'll need. A meter is a little bit more than 3 feet. And we know that an hour has 60 minutes, each of which has 60 seconds. Hey, did you ever think about this before? That's where they get the numbers from. What does the word minute mean? Minute. You take the hour and you chop it up into 60 minute little pieces. So there's the minutes, and then there's the second minutes. Because you chop the minutes up again, you got minutes and second minutes, but it's annoying to say second minutes, so they just call them seconds. That's where that comes from. Let's convert now. So I've multiplied by all 3 necessary conversion factors all at once. Because what am I really doing? According to my statement a moment ago, this is just the number 1. If the numerator is the same as the denominator, this is the number 1. So by multiplying this quantity by 1, I have not changed it. Same thing here. If 1 meter is equivalent to this many feet, then that ratio is just the number 1. So I've multiplied by 1 3 times. That doesn't change the quantity. It just casts it in a different form. It just puts it in different units. And notice I've been careful to arrange things so that the units cancel the way I want them to. I want to get rid of miles and turn them into feet first, and then turn the feet into meters. Because ultimately, I want my units to come out as meters per second per second. So the second's okay. I don't need to change that, but I need to convert the hours into seconds. So if I've got an H downstairs, I need to put an H upstairs here. That's how I knew to say 1 hour on top, 3,600 seconds on bottom. Same thing with the feet and the miles. I want to get rid of miles, so I put the miles on the bottom. I've crossed out everything that cancels and pairs there. Then you plug those numbers into the calculadora. Here is the acceleration of that Porsche in SI units. And a lot of you are thinking, hey, that's a familiar number. 9.6 is very close to 9.8. So we'll get to that number in a second. But you could say it's 9.6 meters per second. Nobody ever says that. Usually you hear it said this way. It's 9.6 meters per second squared, which really just means 9.6 meters per second per second. This number tells us that when that Porsche has got the pedal to the metal, at least for the first few seconds, it's picking up speed at a rate of 9.6 meters per second every second. Let's just round that to 10. How fast is that car going after 3 seconds? Well, it picked up speed at 10 meters per second every second, and it was doing that for 3 seconds. It's probably going something like 30 meters per second, which is in fact a little over 60 miles per hour. All right, next up is probably the most familiar acceleration, the one that we'll talk about most often this semester. I pulled this graphic from a very popular book that's been around for a while called Conceptual Physics by a guy named Paul Hewitt. And that was actually the very first physics book that I was ever acquainted with, and it got me into the subject. I think that's true for a lot of people that went into physics. Anyway, his book has lots of silly little fun cartoon drawings that are actually pretty informative. So here's somebody who's thrown a rock straight upwards until it reaches its apex, and then it falls back down. And you can see that the position of the rock is marked at 1 second intervals. This is very similar to some of the motion diagrams that you'll see in chapter 1. And the author has also indicated the speeds of the ball or of the rock at those various times. So you can see that the ball was thrown upwards at 30 meters per second, which is over 60 miles an hour. So this is a little unrealistic. I don't know if anybody can throw a rock straight up at that speed. I certainly can't. But 1 second later, it's slowed down to 20 meters per second, but still rising. Then it's going 10 meters per second, 1 second later. And finally, a second after that, it's reached the apex and it has a speed of 0. Then 1 second after that, it's moving downward at 10 meters per second, and then 20 meters per second, etc. So is it fair to say that gravity has the effect of causing something to speed up by 10 meters per second every second? Well, that's only true if it's falling down, and it's falling straight down, because on the way up, its speed is actually decreasing by 10 meters per second. So which is it? Does gravity make the speed increase by 10 meters per second every second, or decrease by the same amount? And we can circumvent that difficulty if we talk not about the speed, but about the velocity. Because if you call up the positive direction, so now I'm using the letter Y, let's talk about motion along the Y-axis, that's customary in these classes. If up is the positive direction, then when the ball or the rock is first thrown, it has a positive velocity, and the positive velocity is decreasing. So it decreases from 30 all the way to 0, and then it continues to decrease. He's indicated the speeds here, but if we want to include sign, we would say that the velocity is now -10, and then -20, etc. So really the velocity is decreasing the whole time. And we can say that the effect of gravity is to cause the velocity to decrease by 10 meters per second every second. And that's what we would call a uniform acceleration, meaning it's the same everywhere. That's kind of interesting, right? That whether the rock is here or up here, it's still slowing down, or its velocity is still decreasing at a rate of 10 meters per second. Now you can imagine that if this person was capable of launching this rock, not at human speeds, but at like the space shuttle speed or faster, then by the time it gets way far away from planet Earth, way out in space, it's probably not going to decrease its velocity at the same rate, because the gravity out there would be weaker. And we're going to talk a lot about that. But for the first half of the semester, we don't have to worry about that. We're only looking at problems that take place near the surface of the Earth, where we pretend that the free fall acceleration is the same everywhere. Keep in mind, though, that when you go to the top of a nearby mountain, even Mount Baldy, for instance, the free fall acceleration would be noticeably less. Not by much, but it would be measurable. Okay, so let's calculate that acceleration, because it is an acceleration, it's a change in velocity, but it's a very special acceleration because it's due only to the gravitational field. This would be true if there were no air drag and no wind. It's true in a vacuum. And that's why we give it the special name G. G is an acceleration. It has units of meters per second, but it's a special acceleration. Okay, well, acceleration, or at least average acceleration, by definition is change in velocity over change in time. Let's start by picking these two times, the 6-second mark and the 7-second mark. The final velocity would then be -40, negative because it's moving downwards. So final is -40. And the initial velocity over that time interval would have been -30. So subtract -30 from -40. Well, that's like adding 30. You wind up with -10. Just like I said a moment ago, the acceleration is -10 meters per second. The velocity decreases by 10 meters per second every second. And the word decrease is why that minus sign shows up here. Let's do the same thing, but over a different time interval. How's about from 2 seconds to 3 seconds? So the initial time is 2 seconds. The velocity there is +10. It's going up. The final velocity is 0. It stops for a moment. So final minus initial gives us, again, -10 meters per second. So it doesn't matter which interval you use, you're going to get the same value, because by assumption, the free fall acceleration, or G, is uniform, meaning it's the same at all points along the trajectory. Now, it's actually a little faux pas to have the minus sign here, because most books do it the way your book does it, which is this. Let's use the letter G to represent the absolute value of the free fall acceleration. So from now on, G will always be positive 10 meters per second. And I've written here the more precise value of 9.8. Don't get too attached to this number because it really depends where you are on the Earth. Believe it or not, a G is a little weaker at the equator than it is at the poles of the planet. The reason for that's a little sophisticated. We are going to look at that later in the semester. But if you went to the North Pole, you would actually weigh a little bit more. If you had a really precise scale that would give you your weight out to like 1,000th of a pound, you would definitely see the difference when you weighed yourself at the North Pole. Okay, so G is an acceleration. It's the acceleration of free fall. You can go to a website. Here's one. It's a government website. Enter your latitude and your longitude and figure out what the local value of G is. And not only does it take into account your latitude and longitude, it also depends on your altitude. Like I said, if you're on the top of a mountain, you're a little farther from the center of the Earth. The gravity is going to be a little weaker there, and the free fall acceleration will have a slightly lower value. So I just entered coordinates that are approximately correct for Long Beach and Lakewood. The location of our beautiful campus, which I'm actually missing very much, more than I expected. 34, we're about 34 degrees north of the equator. And here's a fun fact. If you head straight north, if you're in a car driving due north on a freeway, you have to drive 69 miles before your latitude increases by 1. And we know that to get to the North Pole, that would put you at 90 degrees north latitude. So 90 times 69, that's how many miles you have to drive to go from the equator to the North Pole. We're about 118 degrees west of Greenwich, England, the prime meridian. And this is what the computer spat out. Now they're giving it in a different unit, a milligal. Gal is named after Galileo. I believe a gal is a centimeter per second. We'll use that unit later, but 1 meter per second squared is 100 centimeters per second squared. They're actually giving it in milligals, thousandths of a gal. So if you convert, that's this number right here. Notice if you were to round this to 2 digits, it would be 9.8, but it's actually a little bit less than 9.8 where we're living. Okay, now let's watch these two fabled videos. If you have a hard time believing that everything would actually pick up speed at the same rate, if you could get rid of air drag, because we know that if you drop a feather off a building, it's not going to pick up speed very quickly at all. It'll float slowly all the way down, but a bowling ball will get faster and faster all the way until it hits the ground. But those two things, the feather and the bowling ball, would behave identically if you could get rid of the air. Many of you know this, but if you've never seen it before, it's kind of breathtaking the first time. This video was either filmed on the surface of the moon back in, I believe, 1969. It may have been 1970, whatever. Or it was filmed on a soundstage in Burbank. But in any event, this is supposed to be, of course it is. This is it Neil Armstrong or one of the other guys conducting the feather hammer drop?
Well, in my left hand, I have a
Let's back up and hear everything he says.
Well, in my left hand, I have a feather. In my right hand, a hammer. And I guess one of the reasons we got here today was because of a gentleman named Galileo a long time ago who made a rather significant discovery about falling objects in gravity fields. And we thought that where would be a better place to confirm his findings than on the moon. And so we thought we'd try it here for you. The feather happens to be appropriately a falcon feather for our falcon. And I'll drop the two of them here, and hopefully they'll hit the ground at the same time. How about that?
You can find a longer version of that on YouTube. Also, you can find several minutes worth of footage of these guys tripping on the moon because they're wearing those unwieldy suits, and I guess the moon's littered with rocks just like much of planet Earth. And when they trip, they drift kind of slowly towards the surface because the free fall acceleration there is significantly lower than it is here. I think it's about 1/6. Here's a modern recasting of that same demonstration. This is with Brian Cox, physicist Brian Cox, and the British Broadcasting Company. You can find this. And you know, it's kind of weird to think about as you watch this is just how far video cameras have come. You know, the footage that we have now is incredible compared to what they could do back then. And yet that video was taken on the moon and we haven't been back since. It's a little ironic. You know, I don't know if I activated the sound, so let me, yes, I did. Okay, here we go.
Galileo's experiment was simple. He took a heavy object and a light one and dropped them at the same time to see which fell fastest.
So always remarkable to see that. There's a longer version on YouTube there. Let's get out of here. Something else I'd like to say about that demonstration. You know, we're used to thinking that heavier objects fall faster because, for instance, a bowling ball will definitely fall faster when dropped off of a building, but most of you probably know that that's because the feather encounters significant air drag. The bowling ball also encounters air drag, but the effect is less upon the bowling ball. So I'll talk more about this as we go through the semester, but does it seem fair to say that gravity pulls harder on the bowling ball than it pulls on the feather? We know that because if you hold one in each hand, the bowling ball feels much heavier. So we know gravity pulls harder on the bowling ball. It's got more mass. Well, then why doesn't the bowling ball pick up speed faster? If it's being pulled harder, it seems like it should pick up speed at a greater rate. But don't forget that the more massive something is, the harder it is to accelerate. If you want something to pick up speed at a given rate, you have to push harder on it. And that's really the content of Newton's Newton's second law, F equals ma, which is really the main result of the entire semester. We just use it over and over again this semester. So those two effects, in a sense, they cancel perfectly. Yes, the bowling ball, let's say the bowling ball is, it weighs 50 times as much as the feather. It's probably more than that. But if the bowling ball weighs 50 times as much, then gravity pulls on it 50 times as hard. But it's also 50 times as difficult to accelerate. So those two effects cancel, and that's why if you can remove the air drag, everything will free fall at the same rate. That's one way of thinking about it. Einstein had a different way of thinking about it. Okay, we're not done talking about this. If you were to graph the y velocity, the vertical velocity of this rock versus time, you'd get something like this. Because I chose to call up the positive direction, that means when the rock is moving upwards, it has a positive velocity. So for these first few seconds, we see all the velocities are positive numbers, but you'll see that they are decreasing. You can check that every second they decrease by 9.8 meters per second. So the velocity is decreasing, and then this is the crossover point between positive velocities and negative velocities. So that's when it reaches the apex. It was moving upwards with positive velocities. Now it's moving downwards with negative velocities. Notice that on the way up, the length of this line segment is decreasing, and the length of this line segment is the absolute value of velocity. That's the speed. So you can see that the speed is decreasing, and then the speed is actually increasing. See how the length of this line segment is increasing? That's the absolute value of the velocity. The velocities may be negative, but if we take their absolute values, we see that the speeds are actually increasing. But one overarching statement you can make is that the velocity is decreasing the whole time. It may be that the speed decreases on the way up and then increases on the way down, but the entire time the velocity is decreasing. So one question that stumps a lot of beginning physics students is, does the rock still accelerate at the top? Is the rock accelerating at the top of the trajectory, at the apex? And perhaps the best way to understand the answer is just to look at the graph. Isn't the slope of this graph the same the whole time? The slope never changes. The slope is always negative 9.8 meters per second. So the rock may not be moving at the top. Just for a moment, its velocity is 0. Now, how long of a moment? Again, it's infinitesimal. It spends no finite amount of time at that velocity because the velocity is always decreasing. So it's okay to say perhaps that it's not moving for a moment, but it's still accelerating, because what is the slope right here? The same as the slope everywhere else. It's 9.8, negative 9.8. Okay, there's one other way you can think about acceleration, or at least one that comes to mind at the moment. That's concavity. You can see the acceleration in the position versus time graph. I mentioned that all the information in the velocity graph can be gotten from the position graph. All you have to do is take the derivative of this graph to get this graph. Well, the same is true to go from velocity to acceleration. I didn't do that yet in this PowerPoint. I didn't talk about acceleration as the instantaneous rate of change of velocity. I did define average acceleration as delta v over delta t. But if you do the same limiting process that we did for delta x delta t, you would arrive at the conclusion that the slope of the tangent line for velocity is the acceleration. So acceleration is the time derivative of velocity, and velocity is the time derivative of position. So if all the information in this graph is contained in this graph before we take the derivative, and all of the information in this graph is contained in this graph, that means that all of this information is contained in the position versus time graph. We should be able to infer the acceleration from the position graph. And that's what the concavity is. And it's really not very difficult. If you just examine what's happening to the slope here, all of the slopes of the tangent lines here are positive, but that slope is increasing. What does the slope of position versus time give you? The slope of the position graph is velocity. And since the slope is increasing, that means the velocity is increasing. Well, if the velocity is increasing, by definition, that's positive acceleration. Simple as that. If your velocity is increasing, in the physics definition, that's positive acceleration. So positive, an increasing slope means that the graph is scooping upwards. It's got an upward scoopiness, or in other words, a positive concavity. So if it's concave up, it's positive acceleration. On the other hand, if the slope is decreasing, now it doesn't have to be negative slopes. It is for this particular picture. All of these slopes are negative. That's not the important part. The important thing is that the slopes are decreasing. They're becoming more negative. And if your velocity is decreasing, because remember, velocity is the slope, if the velocity is decreasing, by definition, that's a negative acceleration. But it doesn't have to be negative slopes. It just has to be decreasing slopes. So let's look at another example. Here we go. We've got negative slopes here, positive slopes here, and I think you'd agree that this is concave up. Its scoopiness is up. And over here, it's concave down. But check it out. All through here, slopes are positive. So right here, the slopes are increasing. The steepness is increasing. But then the steepness is decreasing. So remember that if the slopes are decreasing right here, so too are the velocities, because the slope of position versus time is velocity. So if the velocities are decreasing, delta v is negative, acceleration is negative. Simple as that. If the slopes are decreasing, then the velocities are decreasing. By definition, that's negative acceleration. So you can see that it's concave down here. Concave down, negative acceleration. Concave up, positive acceleration. And the point where it switches from scooping up to scooping down, where the concavity switches sign, I believe they call that an inflection point. That's a word I've heard that term really abused lately in a political discourse. Both sides, I hear them using that expression. It's an inflection point. I hope they know what that means. So in this context, it's where the concavity switches sign. That's where the acceleration switches sign. Okay, I've sort of already answered this question, but does negative acceleration mean that you're slowing down? Well, it's the same graph we already looked at. You can imagine that this is the graph of the velocity versus time for an object that you threw straight up into the air. When you first throw it upwards, it's got a positive velocity, but it's slowing down on the way to the apex. So the velocity is decreasing. And when it gets to the top, it stops for a moment. And then on the way down, see how the slope is still negative. It's still a negative acceleration, but the absolute value of the velocity is increasing. The velocity is decreasing, hence negative acceleration. Anytime your velocity is decreasing, that's negative acceleration. But the absolute value of the velocity is increasing, hence the speed is increasing. Okay, just to repeat that, even though I've repeated that a number of times. Yeah, positive velocity that's decreasing, so the speed is decreasing. Here the velocity is negative and decreasing, the speed is increasing. There's a simple rule that will help you sort all this out. Yes, it's true the acceleration is negative at all times. Here's the rule, and I think I was trying to show that rule here. Yeah, okay. What's the sign of the acceleration here? Negative, because it's always negative. What's the sign of the velocity here? Negative. So velocity and acceleration here have the same sign, SIGN. Velocity is negative, acceleration is negative. In that case, we're speeding up. Over here, the velocity is positive, but the acceleration is still negative, so opposite signs, and the speed is decreasing. So that's actually the rule in general. If you're speeding up in one-dimensional motion, that means that V and A point in the same direction. They have the same sign. If you're slowing down, you're talking about these two quantities having opposite sign. That's a good rule to remember. And one way to think about that is to anticipate, again, the major result of this class, which is Newton's second law. F equals ma. Force and acceleration are proportional. Whichever direction the acceleration points, that's the direction of the force. So what would be happening if V and A had opposite sign? Well, that's like saying your velocity has the opposite sign from the force on you. If you're moving to the right, but the force on you is to the left, of course you're going to slow down. And force and acceleration have the same direction. On the other hand, if you're moving to the right and something's pushing you to the right, if the force on you is to the right, so is the acceleration, you would expect to speed up. So it's very intuitive. You already know a lot about physics just by, having a physical body and living in a physical world. And I'm a material girl. Okay, that's it for that stuff. You should be reading as much of chapter 1 and chapter 2 as you can during this first week. And in the next video, we'll move on to the so-called kinematic equations. We'll start making calculations about motion.